M.S. Ramaiah University of Applied Sciences.
Hello students, let us discuss the experiment Design and Test Oscillator Circuits. Aim of the experiment is to design and test Harley oscillator circuit. Consider that you need to share the secret information with a friend alone, and hence you build a transmitter and receiver at 50 MHz. Then, if you go to stores and ask to give an oscillator, the vendor asks at what frequency. Sinusoidal oscillators are circuits which can be used to generate various frequencies. These oscillators are a part of any communication system. The electrical signal corresponding to our voice can be modulated onto a higher frequency signal and transmitted to a remote place. Oscillators generate these high frequency signals. One of the important circuits required in any communication system is an oscillator. Oscillator circuit plays a crucial role in all modulation circuits. Consider a loop with an amplifier and a feedback circuit. The total loop gain at the frequency of oscillation should be exactly 1. Further, the total loop phase shift must be 360 degrees. This condition is called Barkhausen condition, which guarantees the circuit oscillation. Many types of oscillator circuits are used in practice. If the feedback circuit comprises of RC, that is resistor-capacitor stages, it is called RC phase shift oscillator. Similarly, if the feedback circuit uses LC, that is inductor-capacitor elements, it is called tuned LC oscillator. In this experiment, two tuned LC oscillators will be designed and tested for oscillation, namely the Harley oscillator and the Colpitts oscillator. The apparatus required to conduct the experiment are DC regulated power supply, breadboard, and designed resistors and capacitors, CRO, and connecting probes. The circuit diagram for Harley oscillator is as shown. Procedure for design the oscillator and amplifier used in the oscillator. The amplifier design. Amplifier used in both Harley and Colpitts oscillator circuits is designed as follows. Observing the output characteristics of a CE amplifier from the manufacturer's data sheet of SL100 for a VCC of 10 volt, choose the Q point as VCE is equal to 5 volts, IC is equal to 2 milliamps. Also observe that beta is equal to 100. VE is equal to VCC by 10, which is equal to 1 volt. RE is equal to VE by IE, which is equal to 1 by IC, that is equal to 500 ohms, nearly equal to 470 ohms. KVL in the collector to emitter loop gives VCC minus ICRC minus VCE minus VE is equal to 0. Hence, RC is equal to 2.2 kilo ohms. VB is equal to VBE plus VE, which is equal to 1.7 volt. That is equal to VCC R2 by R1 plus R2. Choose R2 equal to 4.7 kilo ohm. Then R1 is equal to 22 kilo ohm. Design of the Harley oscillator tank circuit, that is feedback circuit. Let FO is equal to 100 kHz. Choose L1 is equal to 1 millihenry. L2 is equal to 2.2 millihenry. Then L effective is equal to L1 plus L2, which is equal to 3.2 millihenry. The oscillation frequency FO is equal to 1 by 2 pi square root of L effective into C. Hence, C is equal to 800 picofarad. Experimental procedure to obtain oscillator output. Connect the circuit as shown in figure. Vary the pot R 10 kilo ohm to get the output waveform V out. Note down the frequency and amplitude of V out from the CRO. Compare the design and experimental oscillation frequencies and write the amplitude of oscillation from the CRO.
Hi students, the name of the experiment is Design and Test Oscillator Circuits. In this experiment, we will design a Harley oscillator and we will verify if the oscillator is giving a sinusoidal waveform. The apparatus used in this experiment are DC power supply. This is DC power supply. This is first source. This is second source. This is switch on switch off button. This is positive of one of the sources. This is negative of the source. This is positive of second source, negative of second source. These two are used for voltage setting and this is used for current setting. Voltage can be adjusted in coarse or fine manner. In this experiment, we will use one voltage source. Oscilloscope. This is CRO, digital oscilloscope. This is used to check the waveforms from any circuit. We have two channels. Each channel can show voltage as a function of time. The voltage scale can be adjusted using these buttons. This is used for time adjustment. These two control the position of the vertical movement of the waveform. This controls the horizontal movement of the waveform. Breadboard. Here, starting from this end to this end, all the dots in one row are one connection. Again, from here to here, the complete second row represents one connection. Even here also, these two rows represent one connection. Coming to this half and this half, 5 dots in one column are connected. So 5 dots here are connected and it represents one node. Here also 5 dots are joined and it is representing one node. Connecting wires. These are the connecting wires used in this experiment. They can be used to connect various components required to form the circuit. Resistors. These are the resistors used in this experiment. This is 22 kilo ohm resistor. This is 4.7 kilo ohm resistor. This is 2.2 kilo ohm resistor and this is 470 ohms resistor. Capacitors. These are the capacitors used in the experiment. This is 47 microfarad capacitor. These two are 0.47 microfarad capacitors. Potentiometer, we also say it as pot. It has 3 terminals, out of which for variable resistance we use only 2 terminals. The 2 terminals should be next to each other, not the extremes. To change the resistance, this white color stand should be rotated. It can be rotated. Inductors. These are the inductors used in this experiment. This is 1 millihenry inductor and this is 2.2 millihenry inductor. Transistor. This is transistor. It has 3 terminals. There is a notch here. At the notch, the adjacent terminal is emitter. The next one is base. The last one is collector. Connecting probes. The connecting probes used to connect the CRO and decayed capacitance box DCB. This is plus terminal, this is minus terminal. There are all these 6 dials are used to adjust the required capacitance. This is multiples of 1 microfarad. This is multiples of 100 kpf. This is multiples of 10 kpf. This is multiples of 1 kpf. These multiples are for 100 picofarads and this is for 10 picofarads. Now let's start connecting the circuit as per the circuit diagram. Now let us start connecting the circuit. First take breadboard, then take BJT transistor. Now emitter terminal, let it be in the bottom half. So I am connecting emitter terminal here. Then base, connect to the top half. Collector terminal, put it to this side of the top half. So emitter, base, collector. Now take 22 kilo ohm resistor, connect it from base to supply. So base to supply. So this line we will use it for supply. Next take 4.7 kilo ohm resistor, connect from base to ground. So 4.7 kilo ohm resistor from base to ground. So this wire we will use as ground. Now take 2.2 kilo ohm resistor, connect from collector to supply. So collector terminal to supply. This is 2.2 kilo ohm resistor. Next take 470 ohms resistor and connect from emitter to ground. So this is 470 ohm resistor from emitter to ground. Emitter to ground. Next take capacitors. First this is 47 microfarad capacitor. Connect it between emitter and ground, but make sure the negative terminal goes to ground. So 47 microfarad capacitor from emitter to ground. Next take 0.47 microfarad capacitor, connect from base to separate node. From base to a nearby node. Next take the other 0.47 microfarad capacitor, connect from collector to a nearby node. So collector to a nearby node. Now so take 2.2 millihenry inductor, connect from 1 millihenry inductor to a nearby node. Now take a connecting wire and connect the junction of the two inductors to ground. So junction of the two inductors to ground. Next take DCB, use two connecting wires, one for positive and the other for negative. So this is connecting wire connection from negative of DCB. Now connect the positive of this capacitor DCB to 1 millihenry leg of the inductor. Next connect this side, that is negative of the DCB, to the other side of 2.2 millihenry inductor. So this is other side of 2.2 millihenry. So connect it here. Now take two more connecting wires, from 1 millihenry inductance, give this to input side, that is this capacitor. So from 1 millihenry inductor to input capacitor. Take one more connecting wire, connect from 2.2 millihenry inductor to output side. So output side. Now we need the oscillation to happen. We need the circuit to give the oscillation at the collector terminal. But to get these oscillations, this is not sufficient. So what we do is to include a pot for tuning the output response. So what we do is remove the emitter leg, put it on the top, then insert this pot connection between the removed leg and the original point. So this is the pot. As we tune this, we can have a control on the output signal. Next, we will give supply to the circuit. So take two more connecting wires, connect from positive of the supply and give this to supply line. Next, take one more connecting wire, give this from negative so from negative of the supply to ground. So this is the ground connection and this is the supply connection. Now after giving this DC supply, to verify the output we need oscilloscope. So connect a probe to the oscilloscope's first channel. Now take two connecting wires, connect one of the connecting wires from positive of oscilloscope to output terminal. So positive of oscilloscope is connected to output terminal. Then connect negative of the oscilloscope to ground. So negative of oscilloscope is connected to ground. This completes the connections of Hartley oscillator circuit. Let us start testing the circuit. For that, first in the DCB box keep 800 picofarads. 800 picofarads. Now switch on the DC supply, but make sure the voltage knobs are in the minimum and current setting is in the maximum. Switch on the supply. Set 10 volts as the voltage reading. So 10 volts is the DC supply that is given to the circuit. Now switch on the CRO to verify whether oscillation is happening or not. So switch on the oscilloscope. Now because the output is being seen in the first channel and second channel is unconnected, hide the blue color line by double pressing this one. Next, press an auto set. So there is no output that is visualized here. Now start tuning your pot. As you tune the pot, continuously check the oscilloscope. Now press an auto set if required. Tune the pot such that a sinusoid is clearly visible. So now as you tune this, make sure that sinusoid is perfectly visible. Now this is a perfect sine wave. The frequency of this wave is 96.8 kilohertz. This value can be compared with the design frequency, that is 100 kilohertz. Because this is matching the oscillator, the Harley oscillator is resonating at the designed frequency. This completes Harley oscillator experiment. The design frequency and the calculated frequency are almost the same. Thus the oscillator circuit is tested.
At MSR UAS, we spark your imagination unlike any other.